Let's go over Chapter 6, Practice Part 2. Problem 1. The following molecular equations each show an ionic compound dissolving in water. Show the ionization process by rewriting each one as an ionic equation. If you look at the first one, it's calcium bromide. The process of dissolving in water, we're going from solid to aqueous. So what is actually happening? Calcium bromide solid, so probably crystals, is placed in a beaker that contains water. When the compound is placed in water, the ion dissociates. Okay, so we have now the calcium ion and the bromide ion. Notice that we're releasing two bromide ion because the two apply here to the Br minus ion, the anion. All of these species are dissolved in water, so they are in the aqueous state. Therefore, when we're going to write the ionic equation, it will be CaBr2 solid gives Ca2 plus aqueous plus 2 Br minus aqueous. Okay? If we're doing lithium sulfate now, again, dissolved in water, going from the solid to the aqueous states, here we have the lithium sulfate, solid, crystalline structure, that is placed in a beaker that contains water. Notice that we have here two of the lithium ions, so when they are placed in water, we will get two of the lithium ions here. And the polyatomic ion sulfate that remain as a group, okay? Remember that this here is a polyatomic ion, so do not break it apart. All of these species are in the aqueous state, and when we're gonna write the ionic equation, it will give you Li2SO4 solid gives 2 lithium ion plus sulfate ion, both in the aqueous state. Problem 2. Use the solubility rules to determine whether the following are soluble or insoluble in water. So when compounds are soluble, then they will be in the aqueous state. When they are insoluble, they will remain in the solid state. Okay, so let's take a look. Ammonium hydroxide. In ammonium hydroxide, we have the ion ammonium. When ammonium is present, look at your rule, the presence of ammonia make the compound soluble. Therefore, aqueous. Then we have FePO4, okay? Iron 3 phosphate. For this one, there is no rule in the solubility table. There's no rules for Fe3 plus or PO4 3 minus. So because there's no rule for any of these ions, this compound will be solid and it will be insoluble in water. Lead 2 chloride. So what is lead 2 chloride? Lead 2 chloride is made of the Pb2 plus ion combined with the Cl minus ion in a 1:2 ratio. Okay, so what we're forming is PbCl2. The presence of the ion Pb2 plus associated with the chloride ion make it solid. It's one of the exceptions. Aluminum sulfide. The ion aluminum is Al3 plus. The sulfide ion is S2 minus. Therefore, in a 2:3 ratio you're getting the compound Al2S3. There is again no rules for Al3 plus or S2 minus. Therefore, aluminum sulfide will remain insoluble in water and will have the solid state. Problem 3. Aqueous solution of magnesium bromide and lead 2 chlorate react in a precipitation reaction to form insoluble lead 2 bromide. So, precipitation reaction characteristic, a solid is formed, and the solid here is lead 2 bromide. Okay, this is a solid, and we call this a precipitate. That's why the reaction is called precipitation. The molecular equation is shown here. The first part asks us to show the dissolved ion for each solution in the beakers. So let's do magnesium bromide first in this beaker. So when we have the magnesium bromide, notice that there is 2 bromide ion per magnesium ion. So this beaker will contain 1 magnesium ion and 2 of the bromide ion, all of them in the aqueous state. Okay? The second beaker consists of the lead 2 chlorate. Notice again that here we have the presence of the polyatomic ion chlorate, and we have 2 of them. Therefore, the beaker will contain Pb2 plus ClO3 minus 2 times, and they are all in the aqueous state. Okay, both of these reactants are dissolved because they are in the aqueous state, so they will dissociate in water. Then what do we get? We get the solid of lead 2 bromide. So the solid remain undissociated, solid at the bottom of the beaker, so we will not write the ion, it will remain solid. Along with that, we have the magnesium chloride that is formed. Again, notice that we have the chloride polyatomic ion and we have 2 of them. Therefore, the beaker will contain in solution the magnesium 2 plus ion and 2 of the chlorate ion. Again, the 3 will be in the aqueous state. Now that we have this information, we can rewrite the equation as a complete ionic equation. So complete means that we're going to show all the ions, okay? So let's take a look. What we're going to do is copy what we have in the beakers. We have 1 magnesium ion in the aqueous state, and here notice that we have 2 of them, so we're going to place a 2 here, plus 2 of the Br minus ions, plus in the next beaker we have the Pb2 plus ion in the aqueous state, plus, again, notice here that we have 2 of them. Therefore, we're going to say 2 of the chlorate ion, ClO3 minus aqueous. This gives the solid PbBr2 along with the magnesium ion in the aqueous state plus, again, 2 of the chlorate ions in the aqueous state. This is what we call the complete ionic equation. You showed all the ions dissolved in water, all the dissolved ions, okay? We need to now circle the spectator ions. So what are the spectator ions? Those are ions that do not participate in the reaction. So they will be the same on each side of the equation. So let's look for them. We observe that we have magnesium here and magnesium here, 1 spectator ion, 2 chlorate ion here, 2 chlorate ion here, other spectator ions. Okay? Now that we have the spectator ions, to write the net ionic equation, we're going to remove the spectator ions and bring down everything that we have left. Therefore, what I will do is take these and bring them down, and these and bring it down. And I get that 2Br minus aqueous plus Pb2 plus aqueous gives PbBr2 solid. And this is my net equation. What is the driving force for this reaction? The driving force is the formation of the solid compound. This precipitates. So the driving force is the formation of solid PbBr2. Problem 4. The following reaction results in one water-soluble product and one precipitate. Complete and balance the reaction and show phases to indicate whether the products are aqueous or solid. So let's see what we have. We have silver nitrate and magnesium chloride. So here is our silver nitrate. The silver nitrate is in the aqueous state, so when placed in water will release Ag plus and NO3 minus aqueous. Combined with the silver nitrate, we have magnesium chloride, aqueous again, so when in a beaker in water will release the magnesium ion and 2 chloride ion, all in the aqueous state. This is a double displacement reaction, so what will happen? We need to predict the products. The first product will be the combination of the silver ion and the chloride ion. What happened when the silver ion combined with the chloride ion? Well, in a 1-to-1 ratio, because they have the same magnitude of a charge, we will form AgCl. Okay? Then the next is the combination between the nitrate ion and the magnesium ion. Well, when the magnesium ion combine with the nitrate ion, notice that I have a 2 plus here and a 1 minus here, so I need another nitrate ion in order to form MgNO3 2 times. My next step will be to look at the solubility rules to determine their states. Are they or not soluble in water? You will notice that silver chloride is one of the exceptions, so it's solid, and the presence of the nitrates make this compound aqueous, soluble in water. Now that we have our products, we can write down the result of the reaction. So we will form AgCl solid and MgNO3 2 times aqueous. Again, this is a solid, so will remain in the solid state at the bottom of the beaker, AgCl solid. This one is aqueous, so will dissolve, and I will have Mg2 plus and the 2 nitrate ion in the aqueous state. Do not forget that we need to balance the reaction. I have here 2 nitrates, so I'm going to need a 2 here to have 2 nitrates. By placing the 2 there, I have now 2 silver, so I need to place a 2 here to have 2 silver. And if I look now, my equation is balanced. You can adjust the beaker at the bottom by adding another silver and another nitrate ion here. And here I'm going to have 2 of the AgCl. So let's now write the complete ionic equation and the net ionic equation for this reaction. Let's look at the first beaker. We have 2 of the silver ion aqueous and 2 of the nitrate ion aqueous. Second beaker, we have the magnesium ion aqueous and 2 of the chloride ion aqueous. we are forming silver chloride, 2 of them, plus the magnesium nitrate, magnesium ion, aqueous, and the 2 nitrate ion, aqueous. In order to write the net ionic equation, we need to identify the spectator ions, so let's identify them. Observe that I have magnesium on each side and nitrate on each side. So these are the spectator ions. I'm going to remove them to write the net ionic equation. That will be 2 Ag plus aqueous plus 2 Cl minus aqueous gives 2 AgCl solid. Now remember that when you write an equation, you want the lower set of coefficients. So I have a common factor that is 2, so I can simplify by 2. And therefore, my net ionic equation is Ag plus aqueous plus Cl minus aqueous gives AgCl solid. Again, this is here my net ionic equation simplified. Problem 5. Reactions in aqueous solution, acid-base neutralization. Show the product from the following neutralization reaction, bounds if necessary. Why is this an acid-base reaction? Here is my acid, start with an H. Here is the base, contains OH minus. It's a special case of double displacement reaction. Remember that when a neutralization reaction happens, the products that are formed are water, liquid, along with a salt. The salt is actually the generic name for ionic compound. So it's the same as ionic compound. So you're forming liquid water and an ionic compound. Very important to remember when you write, you're going to form your ionic compound. Again, it has to be electrically neutral. Meaning that the total charge needs to be equal to 0. So let's do it. HCl aqueous is the combination between the HCl ion and the Cl minus ion. KOH aqueous is the combination of the potassium ion and the hydroxide polydimic ion. Water is formed from the combination of H plus and OH minus. When H plus combine in a double displacement with OH minus, we form H2O liquid. The salt will be formed from the combination between the chloride ion and the potassium ion. Remember that you always write the cation before the anion, and you will form in a 1-to-1 ratio. KCl solubility rule tell you that this is aqueous. Again, remember that the state of your salt will be given by your solubility rules. 6. Aqueous sulfuric acid and aqueous sodium hydroxide react to form water and aqueous sodium sulfate. Write a molecular, ionic, and net ionic equation for this reaction. Circle the spectator ions. So let's do it. The first compound is aqueous sulfuric acid. The sulfuric acid, ic ending, come from the sulfate polydimic ion. Because I have a magnitude of the charge 2, I will need 2 of the H pluses to neutralize the charge. This is combined with a base that is aqueous sodium hydroxide. Sodium hydroxide, the sodium ion is Na+, the hydroxide polydimic ion is OH-. React to form water, so we're going to form H2O liquid, and a salt, aqueous sodium sulfate. the sodium sulfate will be the combination between the sodium ion and the sulfate polyatomic ion. Therefore, we're going to need 2 of the sodium ion to balance the charge out. Let's write the molecular equation. Sulfuric acid, aqueous, react with sodium hydroxide, aqueous, to form liquid water and sodium sulfate, aqueous. Do not forget that we need to balance out this equation. Observe that I have 2 sodium here, therefore I'm going to need 2 here to have 2 sodium. I have now 2 hydroxide here, and I have 2 hydrogen here. So a total of 4 H's and 2 O's, so I needed 2 here to balance it out. Let's take a look at what we have in our beaker. The first beaker contains a sulfuric acid, ionized, 2 H plus ions and the sulfate polyatomic ions, all in the aqueous state. The second beaker consists of 2 of the sodium hydroxide aqueous, so we're going to have 2 of the Na plus and 2 of the OH minus, all in the aqueous state. The water is liquid, so remain untouched, and we have 2 molecules of water in the liquid state, not ionized. And we have as well in the aqueous state 2 sodium ion along with the sulfate ion. We can now write our complete ionic equation. We have 2H plus aqueous plus SO4 2 minus aqueous in the first beaker, followed by 2 sodium ion in the second beaker plus 2 hydroxide ion in the beaker. This will give us 2 molecules of water in the liquid state plus 2 sodium ion aqueous and the sulfate polyatomic ion aqueous. Let's identify the spectator ion so we can write the net ionic equation. I have 2 sodium ion on each side. I have 1 sulfate ion on each side. So these do not participate in the equation and are called spectator ions. I will get rid of them. I will remove them to write my net ionic equation as 2H plus aqueous plus 2 OH minus aqueous. This is what's left on the left side. Gives 2 H2O liquid. Notice that we have again a common factor, so we can simplify by 2. Therefore, we have now a net ionic equation that is, H plus aqueous plus OH minus aqueous gives H2O liquid. Note that all acid bases neutralization reaction have the same net ionic equation. That is, H plus aqueous plus OH minus aqueous give H2O liquid. Okay? The last question is asking about what is the driving force for the reaction? Well, the driving force for the reaction is the formation of liquid water. Thank you, and let me know if you have any questions.